Welcome to the fourth XACC Tech Talk in our summer series. Before I get to our speakers, I will introduce the XACC program as a special initiative to support novel research in adaptive compute acceleration for high-end computing. Over the last year, we've set up 4 XACC centers at ETH Zurich, National University of Singapore, University Illinois, and UCLA. The centers consist of compute nodes currently enabled with the Xilinx Alveo compute acceleration hardware. These centers are intended as community resources that are available remotely to anyone who joins and participates in the program. This series of talks is intended to highlight some of the research related to the program. If you are interested in research related to adaptive compute, data centers, high-end computing, architectures, tools, applications, database, networking, machine learning, and really anything else, and you would like to take advantage of the program and infrastructure, we invite you to apply to join the program. For more information, you can see the website, that's xilinx.github.io/XACC, and you will also be able to find the archived recordings of these talks on the website. The first speaker today is Hongshi Tan from NUS, and he will introduce ThundeRiNG, generating multiple independent random number sequences on FPGAs.
Hello everyone, my name is Hongshi Tan. I'm a master student from National University of Singapore. Today I will present our latest work, ThundeRiNG, generating multiple independent random number sequences on FPGAs. Pseudo-random number generators, PRNGs, can be a major performance component in many modern applications, such as Monte Carlo simulations and data mining. PRNGs also play an important part in some emerging computing architectures, like probabilistic computer and the quantum computing emulator. We note that the generation of random numbers can be the performance bottleneck for such applications. Taking the Monte Carlo option pricing example, the random numbers are used to decide the simulation passes and the directions in each step. Our emulation shows that the generation of random numbers can take up to 54% of the total execution time. Nowadays, with the increasing problem size and the exponential data growth, those applications need to be accelerated. Therefore, there is a need of high-performance PRNGs. FPGAs has been increasing more applications in data centers and also the general applications. FPGA is also known to be a candidate platform to accelerate the generation of random numbers. There are several reasons. First, comparing with CPU and GPUs, FPGA architectures naturally has the advantage of fine-grained parallelism. Second, the dedicated accelerators on FPGAs is always more resource energy efficient than the general computing hardware. Third, the PRNGs commonly use bitwise operations such as bit truncations, bit permutations, can be efficiently implemented on FPGAs. And more importantly, the reconfigurability features give it enough flexibility to support arbitrary precision integer arithmetic to meet the varying requirements from the applications in the PRNGs. However, accelerating the applications that use the PRNGs is non-trivial. Conventionally, these applications require that the same algorithm is run on each processor, but with different random number sequences. To meet the high throughput requirements, massive random number instances should be instantiated or concurrently to generate multiple sequences of random numbers at the same time. More importantly, the generated sequences should also be independent from each other. Existing study shows that if there are correlation between the sequences, it will lead to a best estimation for the Monte Carlo simulation. Therefore, the generation of multiple and independent sequences of random numbers is important in terms of accelerating the applications that use PRNGs. Despite there are many architectural advantages, we found that existing FPGA-based PRNGs failed to meet these requirements. First, only a few works support the generation of multiple sequences of random numbers in algorithm level, but all of them only leverage the linear recurrence module 2 algorithms, and this algorithm naturally lacks the linear complexity, finally causing the poor quality of randomness. And it means that there are significant statistics false in their generated sequences, which is unacceptable for the real applications. Second, the computation of these works always involves large vector operations, and it needs the on-chip block RAMs to store the intermediate value. However, FPGAs has a limited capacity of the BRAMs, and it limited the maximum number of the instances they can deploy. And the throughput is also limited. Therefore, we can summarize the challenges of generating multiple independent sequences of random numbers on FPGAs. The first challenge is that we need to guarantee the independency among multiple random number sequences, which is that the intra-stream correlations need to be carefully handled. And the second one is to generate random number with high throughputs, which requires to instantiate the instances as much as possible. However, in real hardware, it always limited by the resource capacity. So here we propose the ThundeRiNG FPGA-based FPGAs that can generate multiple independent sequences of high quality random numbers with high throughput. For the first challenge, we propose a novel decoration mechanism for multiple sequences of random numbers. And for the second challenge, we adopt a sharing mechanism to reduce the intermediate resource-hungry stage among multiple instances. I will first introduce the linear congruential generator LCG, which is a fundamental PNG algorithm that we leveraged. After that, I will elaborate the detail of our tool technique. LCG is prone to be an efficient and well-studied algorithm for random number generation, and it has been used in many applications for a long time. And same to all the PNG algorithm, it successfully executes two computation stage. In the first stage, which is the state transition, the state transition functions transits the current state to a new one in the state space. In LCG, the new state action is generated by the following equation: the old state action -1 multiplied with the 1 prime number A, then plus the increment C, and finally module with I. And in the second stage, the output function maps the current state to a random number. Typically, the output function is designed to reduce the statistics false within the state space. For the naive LCGs, it adopts a simple bit truncation in the output stage. Note that for LCGs, selecting different increment C is known to be able to generate distinct but highly correlated sequences. So how to eliminate these correlations? Inspired by the Yale's XACC lemma, which is that the hardness to predict an output for the sequence is amplified when the results of several independent sequences are coupled by the XOR operator. Our decorrelation method is to use the weakly correlated sequences as the correlator to XOR with the sequences generated by the LCG with different increments. Actually, the basic idea is to ensemble a complementary algorithm together with LCG, where the basis LCG algorithm is responsible to reduce the intra-stream correlation, and at the same time, the decorrelators are responsible to reduce the inter-stream correlation. And here we can give two constraints for the selecting of the correlators. As a simple example, we use K1 and K2 to represent a sequence generated by the decorrelator. The first constraint is that the K1 and K2 should be generated from an algorithm that is completely different from linear congruential transformation. And the second is that the K1 should not be strongly correlated with K2, and there is no overlapped subsequences among them. Notice as XOR is known to be able to reduce the statistics bias, there is no need for the decorrelated sequences to have a high quality of randomness. Our experience shows that the naive XOR shift generator is enough, despite it has been known that it's a poor quality one. So the flow of our decorrelation mechanism is shown as follows. Consider that there are two correlated sequences generated by the LCG with the same multiplier and the modulus, at different increments C1 and C2, and also the two sequence K1 and K2 generated by the decorator, which is selected following the constraint as we mentioned earlier. Separately XOR each elements of them together, we can get two new uncorrelated sequences D1 and Z2. Our decorration mechanism is supported by the theoretical analysis, and we also validate the conclusion by empirical testing. If you are interested in them, you can find the details in our paper. And so far, we have one method that can generate multiple independent sequences of random numbers, and the challenge one is solved. To achieve a high throughput or a large number of instances are required. However, since the state transaction in each independent generators requires a large bitwise multiplier, which is contrasted by the DSP size in the FPGA, the number of the independent instances that can be implemented is limited by the available number of the DSPs. So towards the high throughput, our decoration methods also give us a possible way to reduce the consumption of the DSPs. Here, let me elaborate our state sharing mechanism. Our state sharing mechanism is based on a revision of the linear congruential generator. Different to the original LCG transaction is that after the LCG transactions, we add an addition transaction. The addition transaction form a new sequence W, where the elements Wn is calculated by the xn at one integer h and modulo with I. Here we can derive the combined transaction between the Wn and the Wn minus 1. The combined transaction is with the same form as the original LCG transaction. Setting different h in the addition transactions will let the elements in the sequence W to be the same with the elements generated by the LCG with different increments. It can also explain why LCG sequences with different increments is highly correlated. And that is, there is an addition transaction which is a linear relationship between them. And following the help doubling of thermal, we can derive the constraint for the selecting of the integer h, which is that the h should be an even number. These revised LCGs give us another way to generate sequences similar to the LCG with different increments. That is very like tree structures. So we refer the base LCG transition as the root state transactions, and the addition transactions as leaf state transaction. Each addition transactions using a distinct integer h to transit the same root states and then get the distinct output. It also means that the root state is shared when generating multiple sequences of random number. So comparing with the non-sharing generations, where n instance need n times multiplications and n times additions in each step, our sharing generation only need one multiplications and n minus n plus 1 times additions. It significantly reduced the required number of multiplications and the corresponding hardware resources. In FPGA implementations, the root state transactions will be the only one modules needs the DSP slices to construct the multiplier. Therefore, the number of available DSP slices is no longer the limitation of increasing the parallel instances, and we can instantiate a large number of instances to achieve a promising throughput. And here the challenge 2 is also solved. Adopting the decoration and the sharing algorithm, we can have the corresponding implementations on FPGAs. And here comes the ThundeRiNG. And the overview of ThundeRiNG's architecture is shown here. It mainly consists of the one root state generation unit, SGU, and several sequence output units, SOU. The root state generation units generate one root state per cycles and dispatch the root states to the sequence output units. After the sequence output unit receive the root states, it will perform the leaf-state transitions by the inside leaf-state transition units, and there is also a random rotation-based permutation before the states coupling with the decorator. Finally, the random number is output to the application logic. To achieve the maximum performance, we also adopt several optimizations to get an optimal performance. The first we optimized is the dependency problem in the root state generation units. Here we can see the calculation of the root state action is dependent on the parent state's action -1. Therefore, these correlations cannot be pipelined, and due to it has a very large bitwise. It needs 6 cycles to generate one output. The dependency problems makes the root state generation unit to be the bottleneck of the throughput for the entire system. So here we found one good features of the LCGs, which is the arbitrary step jump height, which means that we can get the recursions between the xn's and xn -6. Adopting these factors, we will construct 6 multipliers, starting the advanced 6 jump height recurrences from the neighboring states. And the outputs of these multipliers is reordered to match with the original sequences. After that, the root state generation units can easily generate one root state in one cycle. The second optimization is to improve the kernel frequency. Higher frequencies means better performance. However, sharing the root states for massive number of SOZs introduce the high fan-out problems. To solve this problem and improve the frequency, we adopt a chain topology to connect the root state generation units and the sequence output units. And we also look back the aggregate results to keep the memory access engine too close to the physical interface, which can make the routing more easier. With the above approaches, when implementations with 500 sequences of units can run at 400 MHz, which almost double the frequency. So now all the main techniques of ThundeRiNG have been introduced, and here come to the evaluation. We implement our designs and conduct a comparison with the state-of-the-art works on the following hardware platform. And for FPGA implementations, it is conducted with the Arrow U250 accelerator card, and we using the P100 GPUs as the baseline for the performance comparison. So we first conduct the quality is very crucial for the real applications. So we first conduct the evaluations of the quality of the randomness. It includes 2 aspects: the intra-stream correlation and the inter-stream correlation. For the evaluation of the intra-stream correlations, we follow the evaluation approach in the state-of-the-art works to apply the BigCrush test suite, which is the most stringent empirical testing suite. And we also adopt the pass-rand test suite and the complementary test for evaluating the potential long-range correlations. For the evaluation of the intra-stream correlations, we first interleave the multiple sequences. For the evaluation of the intra-stream correlations, we first interleave the multiple sequences into one single sequence, and it can transform the potential cross correlations into auto correlations. And then we can adopt the BigCrush test suites on the interleaved sequences. Besides this, we also conduct 3 commonly used pairwise correlation analysis and the state-of-the-art Hemingway's dependency test to demonstrate the to demonstrate the effectiveness of our decoration approach. And the results of the quality evaluation shows that ThundeRiNG achieves the same level of the quality of firmness with the state-of-the-art PNG algorithms. And here we show the resource utilizations and the throughput of ThundeRiNG with varying number of instances. So on the left graph, we can see ThundeRiNG use a constant number of DSP slices regardless of the number of sequences, regardless of the number of sequences to be generated. And in terms of the throughput, the observed throughput is nearly proportional to the number of instances and can be up to 20 terabits per second with 2,000 instances. So in comparison with the fastest FPGA-based PNGs, ThundeRiNG also outperform all the current FPGA-based PNGs significantly in performance as well as the quality of firmness. ThundeRiNG also demonstrates over 10 times speed up compared to the state-of-the-art GPU-based implementations. Even the P100 GPUs has more number of the cores and run at a much higher frequency. To further demonstrate the advantage of ThundeRiNG, we applied it to 2 case studies and then compare the throughput results with the state-of-the-art GPU-based implementations. The first one is to estimate the value of pi, which is widely used performance benchmarking for PNGs. The basic idea is that assuming we have a circle and a square that encodes the circle, then combining the 2 random numbers as one 2-dimension point, this point can be treated as a dot on the flat, and the error can be approximately represented by the number of the points that fill in the flat. Therefore, dividing the area of the circle by the area of the square, we can have one estimation of the value of pi. And the second application is the Monte Carlo open pricing, which is a widely used applications in mathematical financial domain. In this application, the uniform distribution randomness are transformed the Gaussian distribution at first, and it represents random motions on a given path in the constraint of a mathematical model. And in here, both the FPGA-based and the GPU-based implementations using the same model. Each pass integratively updates the results using the random numbers, and finally the results from all the passes are aggregated. So comparing with the state-of-the-art GPU-based implementations, ThundeRiNG delivers 9 times speed up in the estimation of pi, and 2.3 times performance improvements on the Monte Carlo open pricing. So we can see the end-to-end comparison of the 2 applications demonstrates that the ThundeRiNG is able to generate massive independent random number with high throughput, and the FPGAs can be a promising platform for PNG-involved applications. So finally, we have the following conclusions. So ThundeRiNG is an FPGA-based multiple independent random number synchronous generators that provide high-quality random numbers with high throughput. And ThundeRiNG can outperform all the current FPGA-based PNGs significantly in performance as well as quality of firmness. And also comparing with the state-of-the-art GPU-based implementations, ThundeRiNG can deliver up to 10 times performance improvements. And it also shows that FPGAs is a promising platform for PNG-involved applications. So we will further explore the ThundeRiNG to meet the requirement of the approximation-based applications, and the source code is available on GitHub. So we would like to So finally, we would like to thank for the generous donation from Xilinx, and thanks for your listening.
Thank you, Hongshi. We have a question. How fast is reseeding, especially compared to reseeding a GPU random number generator?
Actually, the reseeding is the reseeding is happens in the root state generation unit. So it's very fast. We provide the register for the user to reseeding the entire sequences. But for GPUs, for example, you need to call the jump height of functions. It may be very costly. I think this is also one advantage for ThundeRiNG.
And Hongshi, could you tell me what's the source of randomness for the root state?
Actually, we are designing the pseudo random generator, not the true random generator. So for the true random generator, you need a source to provide the randomness. But for pseudo random generators, it is actually based on mathematical representations. So it's not need a source of the randomness.
Okay, so you write a seed value.
Yeah.
Okay. And I was going to ask one more question. Your IP is open source. So you mentioned on your last slide, and you pointed to the GitHub. So is that HDL? Is it HLS? How could other people use this? Could it be integrated into, say, Vitis easily? How could people reproduce this or use this within their own designs?
Oh yeah, actually we are design the summary is designed by the HLS, so it's very easy to for the user to implement in their own applications. We are going to provide some APIs and more detail about how to use this ThundeRiNG in their applications in the future. Actually, we are also using ThundeRiNG in our current project. So we would be very happy for others to use the ThundeRiNG and give us some feedback.
Okay, thank you very much. The second speaker is Joost Hoosemans from TU Delft, and he will present on Fletcher, a framework for high-performance big data analytics using FPGAs.
So hello everybody, welcome to my talk. My name is Joost Hoosemans, and I'm a postdoc in the Accelerated Big Data Systems group, the ABS group as we call it, and in TU Delft in the Netherlands. Yeah, thanks for the invitation. I'm very enthusiastic to share some of our work that we've done in the lab over the last time. So let's get started. Let's see. Okay, yeah. Small introduction about the lab. It's being led by Professors Allars and Hofstee, who is also an IBM researcher. And we do various work on different layers of the technology stack and on different application domains. And here are some of the people who are working with us. It's me in the middle center, as you can see probably. For today, I want to do a short intro about some of the context that we see and vision that we have for doing acceleration of big data applications. Then I want to highlight two of our technologies, Fletcher and Tidy, show a proof of concept and a demo application that we have, which is actually running on the XACC as well. And then there will be time for some questions. So let's look at some of the context of current day computing. So on the software side, in the old days, computers were really expensive, large machines, and there were many programmers working on them because programmers are relatively cheap. But this has really turned around over the last years because now computers are basically really cheap and programmers are really expensive. So it just makes more sense to just add another couple of racks of computers than it is to optimize your program using highly skilled programmers. So everything in software world is being geared towards making it as fast and easy as possible to get code running on large clusters of machines. So for example, Apache Spark makes basically everybody a cluster programmer. And they do that using all kinds of very high level abstractions and APIs, using concepts like records and tables that are just very accessible to a wide range of people programming them. On the hardware side, things are a little bit different, right? Because we've been seeing data still growing exponentially, and that includes throughput on network side and on storage side. It keeps growing with Moore's law. But the CPU speeds on the lower half, they've been capping off a little bit recently. So there's this gap that's starting to form. And this gap is causing people to start using accelerators. So what we're already seeing now is that some accelerators are being used for some workloads, right? Machine learning, for example. But people are designing more and more of these accelerators, and at some point the CPUs will just be orchestrators that will move workloads between different types of accelerators. But as easy as it is to develop software, very high level abstractions, very quick turnaround time, you can get a program running on a big cluster with a couple of days or maybe weeks. On the hardware side, developing an accelerator is still quite difficult because everything's very low level, very geared towards optimization, bits and gates. So it can take an FPGA designer a couple of months to get a complex application running on, for example, an FPGA. So that's all quite low level. And we see that there's this gap here, right? And it's already large and it's only increasing. And this is the area where our lab, where the apps group is focusing most of its attention. So a lot of the stuff that we do is aiming to try to decrease the size of this gap. Okay, so let's have a look at a big data program. So this is a very simple example, word count, right? So this is on the Spark website. It just counts the number of every word in a big text. So what this looks like inside a big data framework is as shown on the left side. It's represented as a graph, a directed acyclic graph, in which the operations are the nodes, and all of these nodes, they represent some kind of a transformation. And if we look a little bit more closely, then these transformations are very parallel constructs, like a map, which is basically applying a certain function to every element that gets passed to the function. So these are actually constructs that are very suitable for FPGAs. They're very spatial. So in our view, what we can do with this representation of a program is, suppose we build a library of components that implement these nodes. So, for example, a flat map of a split in this case, and the map of a constant, mapping something to a tuple of something with a constant. And if there's a way that we can connect these components in our library to each other and to host memory, then we can basically build an accelerator based on the DAG representation of the program, and we can synthesize that to FPGA. So this is more or less our general idea of how we can tackle big data programs with accelerators. Yeah, so one of the important pieces of software that we developed to do this is called Fletcher, because the challenge in doing something like this is that big data frameworks, they work on these very high level environments like the Java virtual machine and Python, They use strings that are variable length. They use records. And on the hardware side, again, you use bits and bytes. You use AXI normally to communicate data between components. So that it just doesn't match very well. So what Fletcher does is it basically converts the data from the big data framework representation into FPGA oriented streams, as you would call them. We use Apache Arrow as a basis for this, because Apache Arrow is an in-memory representation of data that also allows big data frameworks to communicate between each other. So that if you want to use some data you created in a Java-based framework, you want to process it with a Python-based environment, you don't have to serialize it and deserialize it. So Fletcher is actually also supported on the XACC. You can use it for your big data applications if you want to develop them. Later on, I can tell you a little bit about a demo application using Fletcher that we've also developed, and that's also supported by the XACC. So that's very exciting stuff. So now that you can move, so let's go into a little bit of the internals of Fletcher, or at least what it does. So basically, if you have some data in the arrow format, it has a certain schema which basically tells you what the data looks like. So how many columns does it have? What are the data types? And then what Fletcher does is it generates an interface for your FPGA that your kernel developer can use to talk to your data in terms of rows and elements and an index and a table, instead of figuring out in which byte address a certain piece of data is living and then trying to fetch that from your host memory, right? So it makes developing big data accelerators much easier. This is a publication about it at FPL 19. So now that you can get data on and off the FPGA, there's still a large discrepancy of how software can move data between components and how hardware can do it. Because software can use very complex data types, can use even nested data structures and variable length types. And the way that this maps to memory, which is what you use in software, is always quite clear. There's just one way to do it, and all of the libraries and compilers, they know this. It's all standard, it's specified. But on hardware, it's absolutely not specified at all. Again, you have to use bits and buses, AXI. And the difference is that on FPGA, you don't use the one-dimensional memory. You use buses, wires, and cycles. So each clock cycles, you can transfer one word of information over a certain bus. And how you map your data structure onto those wires, you have to figure it out as a developer. And to tackle this problem, we developed a standard called Tidy that tells you exactly how this mapping works. So how you can map your complex data type onto an FPGA data flow bus. And this is published in IEEE Micro. So to show a schematic of this problem, if you have, for example, this complex data structure that has a timestamp and a couple of strings in a struct, for example, then if you go to software, it's pretty clear. If you see there's a certain way that will look like in your memory, or if you use Scala, it's all defined, and there's libraries who do that and who support this. But if you want to go to hardware, for example, get this data into your VHDL accelerator, how would you transfer it, right? Because every string can be a different length, so you have to communicate, is this the end of the string, is this the beginning of a new string, and there's no standard way to do this. So every HDL developer has to figure this out for himself. which makes also IP reuse very difficult. And actually, if you're creating a large design, the integration of many components together, the glue logic, can be one of the most time-consuming tasks that you have to deal with, and it can be very error-prone. So tidy gives you the exact layout of this data type in what we call stream space, which is basically the wires of your bus and the clock cycles in time. So that if you have an IP core with a certain tidy specification for its input-output, you know exactly how to feed it your data, and you know exactly what it will produce as an output so that you can integrate it easily together. So how you can see tidy is that basically we used to have disk file formats for disk, for how data looks like on disk. Then Apache Arrow was introduced to define what data looks like in memory. And we've introduced tidy to specify how data looks like on data flow design, so with wires, with buses, on FPGAs, or even for ASIC designs. So this is one of the more exciting developments that's coming out of the lab, I think. And for example, an AXI interface, you can express that very easily with tidy. It's really like a superset of what AXI can do. So if this is your FPGA design in the middle, and all of the interfaces between the components and between the interfaces to memory are defined by tidy, and you have basically Fletcher to transfer the data from memory onto your FPGA and back, then you can see how we are starting to build a system that can transparently accelerate big data programs. But we can even do more and think a little bit further, right? Because it doesn't need to be the memory that the data comes from. Maybe it comes from disk. It can be on disk in a Parquet format, for example, which is what they call smart SSD or storage attached FPGAs. We even have already a component developed that is able to decode Parquet, which is a very popular big data file format, into basically a tidy-like interface, which is published at FPT last year. And why does it need to go to memory? Maybe it has to go to a network interface using Apache Arrow Flight format for remote DMA requests. So this is these are components that will help us in the future to build very heterogeneous systems that are more holistic. So then, if we recap all of these components, we have a DAG representation of your program. We have a library of components that can accelerate or just implement the functions of the nodes in these graphs. We have tidy that can connect these nodes together very easily, and we have Fletcher to bring the data to back and forth from the FPGA. So this is how we think we can accelerate big data analytics programs transparently. And so what we actually did is we built a proof of concept for this, where we went from an Apache Spark program to an FPGA accelerator. So that's the first use case that I would like to demonstrate, or at least discuss here, which is the Spark SQL accelerator. And the system that we've built this on is a Power 9 machine with an FPGA card using OpenCAPI. So this is a coherent interface, next generation interface to main memory, so you don't have to explicitly move data back and forth, which is something that we can do because of very generous donation also of the university program. They got us a VU37P chip that is more or less the same as the U280. And what we did as use case is we created a SQL query with some open source data set that filters and aggregates some data. So in this case, a filter is a regular expression, and the aggregation is a summation. And in Spark, this is the graph representation of the program. So in the middle, you can see what it looks like in Spark. And we added a pass to the Spark framework that looks into the graph and can replace a subtree with the accelerated version that we developed, that you can see on the right, which instead of executing it on the CPU, it calls the accelerator that's based on Fletcher on the FPGA. And the results are actually pretty surprising, because this is all very early work. It's not optimized at all, but already we can show an 8 times speed up over CPU workers. And the nice thing about this result is that we can fit enough kernels on the FPGA to saturate OpenCAPI bandwidth, which is actually 25 gigabytes per second. So this is much higher than PCI Express, for example. And all of this with very early tools and not very optimized implementations. So we're very enthusiastic about these results. You can read more about it in this publication in XACC magazine, which is a very nice, it's like a roadmap article in a magazine style journal. So it's pretty interesting if you're into this stuff. So this is for when we're using Spark. We did another project to try to integrate these kind of accelerators into other frameworks. So for example, these are the results when we're using Dask, which is a Python-based framework, the logarithmic version on the right. And this is results for when we're using Dremio, which is another very popular analytics framework that already uses Apache Arrow internally. So this is for us a very good match. And we've been seeing yes, similar results for these other frameworks too. So for the second use case, I wanted to show you what we did on the XACC cluster too, because we created a big data analytics application using Fletcher for Alveo specifically. And in this case, what we wanted to do is search through the entire English Wikipedia dataset without an index, compressed, by the way. So the way we implemented this is we created an arrow table with all of the titles in one column and the compressed article text in the next column. And then we search through that with a term that can be entered by the user. So on the FPGA side, we we started out with an U200 and mapped 5 kernels to each SLR and distributed the dataset over the DDR banks. So when we compress the dataset, it turns out into 22 gigabytes dataset. So 15 times 1.5 gigabytes. And map that onto an Alveo. And what we did recently is create build scripts to run all of this stuff. So we built all of the tools, we prepared the data set, and set everything up on the XACC cluster. So if you want, you can also try this yourself. So yeah, this is what the design looks like. And in the end, there's a user interface, a graphical user interface that you can use with port forwarding. So then in your browser, you get this interface that you can type your queries into and specify if you want to use a CPU and how many threads, or if you want to use an Alveo. And it has a measuring bar for the power usage. I actually added one for the CPU too. And then the results are that you can search through the entire English Wikipedia with sub-second latency, and this is 5 times as fast than a dual-socket CPU system. So this is one FPGA versus 2 CPUs. And the takeaway from this demo is not even per se the performance, but the fact that you can use Fletcher to create an accelerator like this with a very modest investment in terms of time, because Fletcher does all of the hard work for you in generating the interfaces to memory, and it just gives you a very easy, accessible kernel wrapper with interfaces for, in this case, there's the titles and there's the text, so that you can start with it right away. So yeah, I mentioned already before, this is all supported on the XACC cluster. You can select the U250 for it, and it uses port forwarding just like the pink web GUI uses on XACC. So if you like, you can check it out. It's on our GitHub. And yeah, as we're nearing the end of the talk, I just want to mention that we're very grateful for the Xilinx, for the support we've received from Xilinx. It's been really instrumental, not only the XACC, but also the boards and the engineering sample chip that we got, and other donations. So really many thanks to Xilinx for that. And of course, all of this work, it's been an enormous collaboration of a lot of master students, PhDs, postdocs. So yeah, it's been a long and very interesting ride, and there were many people involved. So thanks for all of them. And last thing to mention here, if I may take this opportunity, we've actually been seeing some industrial use of Fletcher as well. So people have been contacting us asking if we can add some functionality here or there or do stuff like that. So we've started to put this technology into a startup where we aim to develop this, and we think that it has a lot of potential and there's a lot of value in this. And we really see the accelerator business only going to grow. So we want to be a part of that and try to make this vision into a reality. So we've done the work on various frameworks, also with an intern, and we want to continue with making this acceleration available for more data scientists in a transparent way, so that even data scientists can make use of acceleration in a very easy way. And we aim to expand the library components that we already have. So for example, we have a Parquet component, we have a JSON component, we have a decompressor, but we want to add some more to that. We want to do CSV, we want to add filter pushdown, and do some more work on the automatic integration of filtering and aggregation, and all kinds of very interesting technology in that area. So I think, yeah, that was the last slide for me. I'm very interested to hear if people have any questions.
Thank you very much, Joost. So I see a question: could Fletcher be utilized to drive smart SSD applications where the processing is close to the flash storage? And if it can, how does it compare with other database query offload for smart SSDs like BigStream?
Yeah, that's a very good question. So thanks for that. That allows me to talk a little bit more about that. Because yeah, I think smart SSD, they're going to be really interesting, especially if at some point they're going to have a larger internal bandwidth than the PCI Express that they're currently using. I don't have a lot of experience with BigStream like firsthand, but what I do know is that Fletcher uses, it's really geared towards these much more high-level, almost software-like interfaces. So it can deal with data that's much more complex than anything that we've seen so far. So if you're looking at other even other specifications or DMA generator engines, right? Usually they don't deal very well with variable length data types like strings. So let alone stand with nested stuff and structs and unions and stuff like that. So I think if all of our ideas in tidy are realized, that this will be a technology that is far more advanced than what we've seen so far, and it can not only make life for kernel developers much easier, but it also opens up much more possibilities for automatic integration of IP cores and maybe even automatically firing synthesis jobs, for example. Yeah, I think in the future this is something that I think will be very interesting. So I'm very enthusiastic to see where this will go.
Okay, thank you very much. We're just coming up to time, so I'll start to close the session. But first, I'd like to thank both our speakers again for 2 great talks. A reminder that you are welcome to apply to join our XACC program if you're interested, if you want to get access to the high-end adaptive compute hardware that we've been talking about, and if you'd like to join the community of XACC researchers. And you can find details on the webpage shown on the screen. Finally, thank you to everyone for listening.